Welcome to Math with Professor V. In this video, we're going to learn about the limit comparison test. Now, the limit comparison test is one of my favorites because it's straightforward, it's not too difficult to apply, and it's very versatile. You can use it to test so many different series. So let's look at the statement first and then work through a bunch of examples. That way you're a pro by the end of the video. So it says, suppose the sum of an and the sum of bn are series with, and this is important, positive terms, if the limit as n approaches infinity of an over bn is equal to c, which is a positive constant, so it can't be zero, okay? Then both series converge or both series diverge. So let's kind of break this down a little bit. First of all, I made a big deal that all of the terms have to be positive, meaning don't do limit comparison test for an alternating series, okay? And then the other thing is you take the limit of the ratio of the terms of the two series. As long as you get a non-zero finite number, positive constant, then the series are twinsies. Either both of them converge or both of them diverge. So the actual number or value of C doesn't matter. It could be 1, it could be a half, it could be a million. As long as it's not zero and it's finite, your series does the same thing as the one that you compared it to. And it doesn't matter which is which, but basically they behave the same. And I'm gonna keep repeating that, okay? And the tricky thing is when you're doing sequences in series and you have all these different tests, right? The conclusion of each one tells you something different. So you really have to know the statement, the conditions, and all of that. And I do have a video going through how to know which test to use. I'll link that in the description. But you just got to practice, and you also have to practice explaining it to somebody else, because then you really solidify the thought process in your mind, all right? I know this is tricky. It's scary. It's not like integration by parts where there's just a formula and you just like crank it out and it's a process. You have to logically reason and it can be nerve-wracking, but I'm here to help you. So here we go. Are you ready? This is a fun test, I promise, okay? You're gonna love it. So here we go. Determine whether the series converges or diverges. We have here the sum n equals 1 to infinity of n plus 1 over n cubed plus n. So we can call this an. It doesn't really, matter. All of these terms here, that can be my an. And your job is to figure out what's an appropriate choice of bn, okay? And then here's my huge hint. This is going to save you. Look at who's running the show in the numerator and the denominator. Namely, like what's the highest power term? What's the most powerful term? So if I'm looking in the numerator, I have n plus 1. Nobody cares about poor little 1. So n is running the show in the numerator. And then in the denominator, we've got both n cubed plus n, but it's that highest term that's controlling things, n over n cubed. So that simplifies, right, to 1 over n squared. Don't just leave it like this. We have to make some sort of statement about the sum of bn, right? Because we have to compare the sum. So what do we know about the sum, n equals 1 to infinity? You want to start your index where this one starts, okay? Matchy, matchy. What do we know about the sum, n equals 1 to infinity of 1 over n squared? Well, we know that's a p series. P is equal to 2, which is greater than 1. So this series converges. So you know what? I have a gut feeling this series will also converge, and I'm going to use the limit comparison test right now. Take the limit of the ratio of the terms, and as long as I get a non-zero constant, then I can conclude that my series converges also. And this is the perfect time to use limit comparison test. You can't use direct comparison actually, because I can't show the correct direction inequality. And if you want to know when to use direct versus when to use limit comparison, I have a video on that. But limit comparison is so much more versatile. You can pretty much always use it, where direct comparison you can't. So that's why I just like to focus on this one a lot of the time. Okay, so let's get to the important part. We're going to take the limit now. The limit as n approaches infinity. I'm going to put the terms of our series up top, n plus 1 over n cubed plus n. It doesn't really matter which one's in the top and which one's in the bottom. And then put the terms of the other series that we're comparing it to. in the denominator. Okay, now let's simplify. So this is going to be the limit. N approaches infinity. I'm going to have n plus 1 over n cubed plus n times n squared over 1. And then let's see here, limit n goes to infinity. I'll just distribute the n squared in the numerator. So we'll have n cubed plus n squared over n cubed plus n. Okay, now to take this limit, you have a couple options. Like, I don't know how strict your professors are. If you want to do the little pre-calc shortcut where you just look at the leading coefficient of the highest degree terms, I'm thinking most of the time that's going to be a no-go because we're in Calc 2. Definitely can't use L'Hopital's rule because that's only allowed on differentiable functions. Yep. And these sequences, right, the terms of a series are not differentiable. So don't even think about L'Hopital's rule unless it's like dire. What we're going to do is divide by the highest power of n in the denominator. And that highest power is n to the third. So I'll divide everybody by n to the third or multiply by 1 over n cubed. Same thing. Okay. And then we still write lim, you guys, every step of the way. Don't forget that part. The numerator is going to become 1 plus 1 over n, and then the denominator 1 plus 1 over n squared. And then now as n goes to infinity, 1 over n will approach 0. So will 1 over n squared. And then now I don't have to write lim anymore because there's no more n's. So I just have 1 over 1. That's 1. And remember, what do I care about the value of this limit? I care that it's finite and that it's not 0. I think in some of the videos before, I wrote that 1 is greater than 0, which also implies, you know, it's a finite number, but it's not 0. Either one. Those, I like kind of writing it this way better just because it emphasizes that there's two things that we're considering, okay? Again, I don't care that it's 1. It could be 42. It could be 8. It can't be negative because remember, only use limit comparison when the terms are all positive. Okay, so, but it needs to not be 0. And now this tells me, since I have a finite non-zero number as a result of the limit, that my series is twinsies with this series. They do the same thing. So who did I compare my series to? A convergent p-series. So that means my series converges also. And we have to tell the people. We're going to summarize. So this implies that the sum, n equals 1 to infinity, of n plus 1 over n cubed plus n converges also. And tell them what test you use by limit comparison test. I love a good abbreviation, don't you? I mean, we don't have time to write that all out. Okay, we're going to do more. Okay, we're getting warmed up. Hang in there. You can do this. All right, number 2, we have the sum, n equals 1 to infinity, the square root of 1 plus n over 2 plus n. All right, so think of, this is all an. What should bn be? Well, let's see. What's the highest degree term in the numerator? I have square root of n, basically, right? Who cares about the 1? Sorry, 1. We're not worried about you. We've got square root of n up top, and then we have just plain old n in the bottom. If you simplify that, you're going to have 1 over the square root of n. What do I know about bn? Nothing. But what do I know about the sum, n equals 1 to infinity? Of 1 over, that's not true, I didn't know nothing, but don't forget to write the sigma. That was the point I was trying to make. This is a p-series. What's p? It's 1/2, right? Because this is 1 over n to the 1/2, which is less than 1. So this series diverges. Okay, I want to make a huge distinction right now. Don't forget to write sigma. Because this p-series is a divergent series, yes. Bn, all by its lonesome without the sigma, this is a convergent sequence. And I know you only study sequences just a little bit in the beginning of this unit, and then the rest of the time you're focusing on series. but there is a huge distinction. This is a convergent sequence. The limit as n goes to infinity of these terms is 0. But as a series, when you sit there and add it up, no, it diverges. So when you write Bn, don't forget you need to write a sigma in your justification when you say what it does. Okay, rant over. Here we go. Now it's time to take the limit of the terms of the series given with the terms of this divergent p-series. We can even write consider. So elegant. Consider the limit as n approaches infinity. And then we're going to have now square root 1 plus n over 2 plus n over 1 over rad n. Okay, so this is going to be the limit. N goes to infinity. That rad n is going to flip up to the numerator. So then I'm going to have square root 1 plus n times rad n over 2 plus n. Okay. Since both terms in the numerator are underneath the square root sign, I could put them underneath the same one and then distribute. So this is going to be n plus n squared underneath the radical, and then we have 2 plus n in the denominator. Good. Now to evaluate the limit, we're going to divide by the highest power of n from the denominator. So I'm going to multiply everybody by 1 over n. Same as dividing by n, 1 over n. So here we go. This is limit. N goes to infinity. Now remember, when I put 1 over n underneath the radical, it becomes 1 over n squared. If you take something that isn't originally underneath the square root and you put it underneath 1, you have to square it. Why is that? Think about it. Here's 3. What a sweet little number. If I put it underneath the radical, it's not 3 anymore. But if I square it, then I get back 3. Okay, so that's the idea. All right, so now in the numerator, we're going to have square root n over n squared, right? Because this 1 over n becomes 1 over n squared inside, plus n squared over n squared. And then in the denominator, we're going to have 2 over n plus 1. Okay, let's clean up some more. Limit n goes to infinity, square root, this is 1 over n plus 1 in the numerator over 2 over n plus 1. Beautiful. Now we can take the limit. So as n goes to infinity, 1 over n, that goes to 0. 2 over n, that goes to 0. I have square root of 1 over 1. So this limit is 1. Remember, I need to make sure that it's finite and not 0. And then what does that tell me? That tells me that my series does the same thing as the one I compared it to. So notice here, this time the limit's 1. That doesn't matter though. My series diverges because I compared it to a divergent p-series. So this tells me that the sum, n equals 1 to infinity, of the square root of 1 plus n over 2 plus n also diverges. If you get in the habit of writing that word also, then you'll remind yourself like, oh, when I do limit comparison tests, they're twins. By limit comparison test. Okay, so look back. That first example I did, the limit was 1, but we said our series converged because we compared it to a convergent p-series. As long as it's finite and non-zero, they are twins. And then look here, example 2, again the limit's 1, but this time our series diverges because I compared it to a divergent p-series. Okay, now you might be wondering, what happens if the limit comes out to be infinity or 0? What if you don't get a finite non-zero number? And here's something to keep in mind. That's a U problem, meaning that means you picked the wrong Bn. You either picked something that was growing too fast or not as fast as what you're comparing it to, which is why the limit didn't come out to a finite non-zero number. So if you don't get a finite non-zero number, go back, choose a different Bn, or maybe you need to choose a different test entirely, okay? but you get no information. No information, it's a you problem. You got to fix that somewhere else. Okay. Here's another one. How do you feel? You think you can try this on your own? I feel like you could. I really do. I'm getting that vibe through the screen. I am. Why don't you pause the video, try it on your own. Okay. Did you pick BN? Now, here's the thing. So my students, they're like, do we need to keep the 2? You can, or you don't have to. That's why I love limit comparison test. If you want to keep the 2, go for it. It won't make a difference. And then you have n squared squared. I don't like so many constants, you know. I'm like, just strip it all away. Keep it clean. But it won't make 1 ounce of difference. Okay, highest power of n in the numerator is n to the 1st. Highest power in the denominator is n to the 4th, yeah? So n over n to the 4th, that simplifies to 1 over n cubed. Right now, 1 over n cubed is just a sequence. Don't forget, we are testing series. So we have to write the sum. N equals 1 to infinity. 1 over n cubed. What do we know about this series? It's another p series. P equals 3, which is greater than 1. This guy converges. Do you notice so far, every single problem, we're comparing R series with P series. That's pretty much how it goes. You're usually going to compare to a P series or geometric. That's about it. And P series more often than the other. Okay? So, yes. If your series looks like a P series amped up, you know, with lots of extra fluff, probably use limit comparison test. Okay? Here we go. Consider the limit as n goes to infinity, 5 plus 2n over 1 plus n squared squared over, could that have been crookeder? 1 over n cubed. Limit, n goes to infinity. Are you guys cool? I'm going to flip the n cubed up top and distribute it through there, okay? Hang tight. 5n cubed plus 2n to the 4th over 1 plus n squared squared. Okay, beautiful. What's the highest power of n in the denominator? Why, yes, it's n to the 4th because we have n squared squared. So I'm going to divide everybody by n to the 4th. So we've got now the limit as n goes to infinity. This is going to be 5 over n plus 2 in the numerator. Now, when I divide by n to the 4th, but I put it into something that's already squared, it becomes n squared, right? Because n squared squared is n to the 4th. So what I'm going to have right now is 1 over n squared plus n squared over n squared squared. Did I lose you or you're okay? This n to the 4th becomes n squared when I put it inside these parentheses here because it's already going to square it one more time. Okay, so we can take this limit. 5 over n, that goes to 0. 1 over n squared, that goes to 0. N squared over n squared, that's just 1. So what do we have going on here? Is it a hot mess? We've got 2 over 0 plus 1 squared, which is 2, which is finite and non-zero. Perfect. That's all I needed. So then what does this tell me? This tells me that my series does the same thing as the one that I compared it to, a convergent P series. So this must converge also. They are twins. This means the sum, n equals 1 to infinity, 5 plus 2n over 1 plus n squared squared, and I would just get in the habit right, also converges. You can't write also unless it's the same, you know, by limit comparison test. Good. How are you feeling? I said most of the time you do limit comparison with P series or geometric, okay? More P series than the other. Yeah, I thought let's make it a little spicier, okay? You ready? So here we have the sum, n equals 1 to infinity, e to the n plus 1 over n times e to the n plus 1. This one you also could do direct comparison test with, but this video is exclusively on limit comparison test, so we're not going to talk about such things. Okay, so let's pick Bn. Who's running the show in the numerator? Never the constant, right? Unless that's all that's up there. So e to the n. We love you, e to the n. And then in the denominator, n e to the n. That's running the show. N e to the n. Well, this simplifies. E to the n we can cancel out. This is just 1 over n. What do I know about 1 over n? It's a convergent sequence, but that's not important in the context of this problem. You need to always write the sum of Bn, the sum. N equals 1 to infinity of 1 over n. Oh, we know him. Or her, whatever. This is the harmonic series. It diverges. It's a P series. P is 1, but it's so spicy and special and famous that it gets its own name. Okay. So then I'm getting the vibe then that this will diverge also because it's growing like the harmonic series. Let's see. So consider the limit. N goes to infinity, e to the n plus 1 over n, e to the n plus 1 over 1 over n. Okay, I'm going to do the same aggressive maneuver, but you guys are ready for it. This is going to flip up here, and I will distribute. So this is limit. N goes to infinity, n e to the n plus n over n e to the n plus 1. Good? Okay, we have to divide by the highest growing or fastest growing term from the denominator, which is all of this, n e to the n, believe it or not. So everybody is going to get divided by n e to the n. Ooh, that's fancy, right? I don't know. I feel like that doesn't happen every day. Limit, n goes to infinity. In the numerator, what are we going to have? 1 plus n over n e to the n is just going to be 1 over e to the n. And then here, this is going to be 1 plus 1 over all that. 1 plus 1 over n e to the n. But look, it's so cool, because if n goes to infinity, e to the n goes to infinity. So 1 over something getting big goes to 0. This is also getting very, very big in the denominator, so that goes to 0. Beautiful. This limit is 1, which is finite and not 0. So that tells me my series does the same thing as the one I compared it to. I compared it to a divergent series, so mine diverges also. So this means that the sum n equals 1 to infinity e to the n plus 1 over n e to the n plus 1 also diverges by limit comparison test. Okay? Good. I hope that one was fun. I have 2 more. Yes, I do. Okay, here we go. We have the sum, n equals 1 to infinity, 1 plus 1 over n squared times e to the negative n. Don't have a panic attack. Please stay calm. I know it looks weird. It's okay. You can do this. When I would get like really worked up when I'd see new problems, because I know the feeling, I would just tell myself, okay, like calculus is old. It's been around for hundreds of years. I don't need to invent like new math to do this problem. So I just need to sit here and think calmly and apply real principles that I've been taught, and it will work out. Okay, but you don't need to come up with something cutting edge. Please believe. Okay, who's running the show? I think that's the trickiest part right here. And this all looks very intimidating. It's not though. Just think about what's happening to this term as n gets very, very large, okay? As n gets large, 1 over n goes to 0. So we have 1 plus 0, and it's just being squared. This is not an n. You should know. You should memorize that the limit as n goes to infinity of 1 plus 1 over n to the n, that's e, right? That's our definition, actually. And you can prove that if you use L'Hopital's rule and natural log and whatnot. But anyways, I digress. This is not an n. This is just a 2. I mean, even if it was an n, this is approaching a constant. So good news is this isn't like blowing up or going anywhere crazy. It's just approaching a number. So it's actually not that important. It's not running the show. I know it looks like there's a lot going on, but it's not contributing significantly to the growth or shrinkage of the successive terms. Does that make sense? Who's really important here? E to the negative n. Because you guys, e raised to an n, that's going to really, really change the growth or shrinkage, right, of the terms here. So I'm just going to focus on this, and I'm going to say that's Bn. Bn is e to the negative n. Shall we rewrite it? Would it make you feel better if it was 1 over e to the n? Or perhaps 1 over e to the n? Does that even calm you down just a wee bit more? Because remember, the sum, n equals 1 to infinity, 1 over e to the n, it's not a p-series. No, it is geometric. And that's the other kind of series that we often use for limit comparison tests. I'd say majority of the time it's p-series, and then other option, geometric. That's pretty much it. What do we know about geometric series? Well, as long as the absolute value of r is less than 1, it converges. Absolute value of r here is absolute value of 1 over e, and that is definitely less than 1, so it converges. Did I say that correctly? As long as absolute value of r is strictly less than 1, not even equal to. Okay, and then you're going to be amazed at how beautiful this limit is. Are you ready? I don't think you are. Look at how cool. So we have the limit. N goes to infinity. An is going to go in the numerator, so 1 plus 1 over n squared, e to the negative n. Bn is going to go in the denominator. I'm just going to write it like this, e to the negative n. Oh, they just cancel. Okay, fabulous. And then what am I left with? Just the limit. N goes to infinity. 1 plus 1 over n squared. Oh, and we already kind of talked through this limit together earlier, right? 1 over n goes to 0. This is not an indeterminate form because we have 1 squared. That's a finite number. It's not infinity. Then it would be indeterminate. So this is 1 squared, which is 1, which is finite and non-zero. Look how that just fell into place beautifully. So let's summarize. My series does what? It's twins with this convergent geometric series. So that means the sum, n equals 1 to infinity, 1 plus 1 over n squared times e to the negative n, that also converges by limit comparison test. Okay. I have one more for you, and it's famous. And some people see the trick right away. Not a trick, but some people can spot how to solve it. And then other people need a little hint, need to have seen it once, and then they will remember. I fall into the second category, but it's okay. When I was a student. So here we go. We have the sum n equals 1 to infinity sine of 1 over n. So if you want to pause the video, try this one on your own. Bn is going to be just 1 over n. I know. So what do we know about the sum n equals 1 to infinity of 1 over n? That's harmonic series. It diverges. Okay. And I want to remind you something. Do you remember learning this when you were an innocent Calc 1 student? That the limit as theta approaches 0 of sine theta over theta is 1. That's what we're going to use here. Okay. It also works if you have theta over sine theta, because reciprocal of 1 is still 1. So now we're going to consider the limit as n approaches infinity, sine of 1 over n over Bn, which is also 1 over n. Okay, now you could just straight away say this limit's going to be 1, because as n goes to infinity, these both go to 0. But let's be super precise. You know what I mean? how are we going to bring in the precision factor? We're going to go, oh, well, let t equal 1 over n. Then, as n approaches infinity, what an ugly infinity, hold up. Then we know t approaches 0. So then I can rewrite this as the limit as t approaches 0, sine of t over t, and then this is a limit that you learned in Calc 1, very famous. This is 1, which is finite and non-zero, which tells me what? It tells me that my series behaves the same as the one I compared it to, which was a divergent harmonic series. So this means that the sum, n equals 1 to infinity, sine of 1 over n, also diverges by limit comparison test. Okay, so that concludes the video. Give it a thumbs up. Let me know in the comments down below if there's another test in particular like that you're struggling with. I have a whole playlist on sequences and series, and I've gone over every single test in there, and also I have like strategy on testing series videos on that. But if there's anything else that you just feel like you need more examples for, please let me know in the comments. I'm happy to make updated videos or just work through more examples, because I know how difficult this unit can be. But once you get a hang of it, it's really fun actually, because it's not so computationally heavy like some of the integration techniques. So kind of enjoy it as a break from that in a way. But I know it's scary because you kind of feel like you're just free floating in space, having to come up with which test and build the argument. It's not as formulaic. I get that part. So yeah, it can be scary, but it's manageable. Okay. Just remind yourself that you can do it. Don't forget to give the video a thumbs up. Did I say that? Subscribe if you haven't already. And then you can also follow me on Instagram, TikTok, Math with Professor V. And I also have video lectures on differential equations, linear algebra, all sorts of good stuff if you're going to be taking those classes anytime soon. Thank you guys so much for your support. I really do love you all. I'll be back sooner than later. Bye.